So, what are the properties associated with this? So, the objects, when they stretch or regain their shape, when they regain the shape, they are stretched when force is applied and attain their shape back. So, the property is called elasticity. You apply a force, it stretches, and then you take away the force, it comes back to its original shape. And this kind of deformation is called elastic deformation. It is elastic deformation is caused. Whereas if there is a permanent, so these are all a temporary deformation. Elasticity is a case of just some temporary deformation, not permanent. Whereas there is a permanent deformation also possible. Permanent deformation is possible in case of plastics. Those substances are called plastics, and the property is called plasticity. Plasticity is the property. If you take mud and putty, these are all examples for near ideal plastic. Permanently, we can deform something. You cannot get back its original shape. So, when we see this elasticity, why it is important? It is important because it plays a great role, major role with engineering designs of large structures and things like that. Plays a very important role. So the design engineers focus, try to understand more about the elasticity, the nature of especially the buildings that are built with concrete or steel, even aerodynamics. Aeronautical engineers are also try to study about the properties of materials, how to make an aircraft lighter. At the same time, it has to be strong. So, what should be done? And what kind of force will act on them? If some forces act on these bodies, or the buildings, or be the aircraft, and how will the how will it get deformed? How does it affect the structure of the building? So that understanding this makes it important for your design aspect, engineering. To begin with, we are going to see something called stress and strain. What are they? Let's suppose you have a body, you have an object which is in static equilibrium. And I'm applying some force on it. I'm going to apply some force on this body. Okay. So, depending upon the nature of the material that is here, so if it is a concrete structure, if an iron or something, the force is not going to deform it. The amount of force, depending upon the nature of the substance and the amount of force, the deformation will change. You apply a huge force on some soft material, it is going to get deformed much. So the deformation, which is caused due to the force applied on the object, say the nature of the material. Depending upon the nature of the material, the deformation will vary as well. Now, you're applying the force. A force is being applied. What happens to the object? Let's suppose it is going to get deformed. Okay. This is your object. Now, this force that you're applying can be called as deformation, deforming force. Can you give me an example of deforming force? Can somebody give me an
Punching
example
clay.
of
Punching clay.
punching
Clay objects.
clay objects? Could you brief it a little bit more on that? What happens?
So when you punch, for example, clay toy, a clay car creates an impression which shows the presence of deforming force.
Or a car hitting into a post.
Hitting into a post. Okay.
Pulling a rubber band.
Pulling a rubber band. Yeah. Okay. Okay. Well, so all these are examples where the force applied is going to deform. So the force which when applied on an object is going to deform it can be, you can call it as a deforming force. When there is a deforming force acting on it, there will also be another force acting called a restoring force, which will try to restore the body to its original form. Okay. So for every deforming force, there is going to be what? There is going to be a restoring
Restoring.
for every deforming force acting on an object. So what is the role of the restoring force? What is
Bring it back to its original
yeah.
shape and shape. Sir, so if example, like if you're taking the clay impression, the
Hmm.
forming force is much greater than the restoring force. That's why it doesn't return to its original.
Not only that, like I said, it also depends upon what? Nature of the material. Yes.
Okay.
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 So now, if if there is a deforming force, we see that there is going to be a restoring force, right? Now, they are going to be opposite direction. So if it acts, one acts in this direction, the other one is going to act opposite to that. Right? The directions are going to be opposite to one another, right? One tries to deform, the other one tries to restore. So now, the restoring force acting on the body for a unit area. So whatever total area is there, if you divide the whole area, total force by the total area, okay, we call it as this ratio is called as stress. This is what is called as stress in terms of physics. Okay, all right. So how do you measure it? So this is your force by area, the amount of force which is going to act on an object. The restoring force is going to be equal in magnitude. So
Yes, sir.
So here,
Uncle, isn't that just pressure?
hmm,
Isn't it
isn't it
just
just
pressure?
pressure? It is pressure. So it's other form of pressure. Force by area is nothing but pressure also. Correct. Now, if you look at it, imagine this force acting as a normal to the cross-sectional area. So, what do I mean by it? Let's take the case of a cylinder. Imagine I have a cylinder. Um, any cylinder that you can think of,
Water tank.
cans, Coke cans, small. I think you don't use such. You guys use them, energy drink or some juices, refreshment
Yes,
juice
sir.
cans. So you
Yes.
crush. Let's say you're applying some force. You're applying a force which is normal to the cross-sectional area. Cross-sectional area is the circular part, right?
Mm.
The force is applied normal to the cross-sectional area, and where A is the area of the cross. So the stress is now nothing but F by A gives you the stress. So what is the unit now going to be?
Pascal.
Newton per meter square or even Pascal. Yes. Okay. So what will be the dimensional formula? The one is going to be Newton is what? Force into mass into acceleration. So ml e minus 2 times m minus 2 meter per meter minus 2. Area is length minus 2. So you have
So
L and L
N
minus
negative 1 T minus 2.
L minus 1 e minus 2 dimensional formula. Is this clear?
Yes, uncle.
Yes, sir.
Hope this is clear as well. All right. Next step. So by the application of force, a solid can be changed in respect to its dimensions. Okay. So you can apply the force at an angle, so perpendicular, normal. If you apply it to it, what happens is either you can elongate it this way, um, you know, you apply the force externally. What happens? You're pulling it from both the sides. What will happen to that can? Uh, suppose let's
Both sides.
uh,
It
It
will
will just
jump a bit and then break off.
so you're applying a force in this manner on both the sides. What will happen to this? It's going to
rip apart.
elongate. You're pulling from both the sides. So suppose its original length is L. Now the changed one is going to be L plus delta L will be the new length after the application of the force acting outwards on both the sides. Okay.
Okay.
Similarly, not only this, we can also think of applying the force sideways. So if you apply a force in such a way that it gets tilted, you're crushing it, something. Can this happen? Have you seen something, the shapes being changed like this? No?
Yes, sir.
We might have some occasion.
A stack of papers, for
Yeah,
example.
yeah. Totally. Okay. So here, if you look at the force is being applied around the edges. So when the forces are acting in this direction, that is when the deformation takes place like this. You can see that is the shape is moved by an angle. Deformation is by some angle. So when in the first case, the stress, if you look at the stress acting on the cylindrical body, okay, the stress here is called tensile stress. What is it called? So the stress on this cylindrical body. What is it? Stress. What is the stress otherwise also called?
Tensile stress.
Tensile. What is it? What was the definition we said? The ratio of what to what and what? Anybody? Anyone?
Force and area.
No.
Uh,
Anybody? Not even.
Sir, you were
Hmm? Nobody?
the ratio of tensile stress, right?
Plus what's ratio of what to what?
Stress was ratio of force and area, right?
Force and area. That's what present told.
What was it?
Restoring force.
Oh,
It's
okay.
not just force to area. Force to area is nothing but the pressure.
Yes, sir.
Restoring force to the area is what your stress actually means, and this is nothing but your tensile stress. What you're seeing in the case of a cylinder when the force is acting normal to the cross sectional area. On the other hand, when you okay, here what are we trying to do? We are trying to stretch it. The forces are
Yes.
applied in such a way that the deformation is happening as a stretch. So in this case, you can call it as a tensile strength. Right? When you're crushing it so that it is going to compress, you can call it as a compressive stress.
Okay.
During compression, the same stress becomes compressive stress. When you stretch it, it's going to be called
Tensile.
tensile stress. Is this part clear?
Yes, sir.
So in both the cases, so what will happen in the tensile stress or compressive stress? Will there be an impact to the length?
Yeah.
Yes, sir.
There is going to be an impact with the length.
In tensile stress, it will be longer, and in compressive stress, it will be shorter.
Yeah. So since both these stresses are affecting the length, we can also call them as longitudinal stress because it affects the length. Can we accept this or should we oppose this?
We can accept it.
Yeah. This is called longitudinal. So then, so the change, so L became L plus delta L or L minus delta L, isn't it?
Yeah.
Yes, sir.
Change in length was nothing but this. So if you see, now if you look at this delta L, what is delta L?
Length in length.
Change in length. Difference in length.
Yeah. So the change in delta L with respect to L is called, we call it as strain. That is called the strain acting on the body. Now, since this is with respect to the length, what can we call it as? Can we call it as longitudinal strain? Just like longitudinal stress?
Yes, sir.
And we can call it only if you want, otherwise, we will not call it. We'll call it something else. Okay.
Yes, Sakul.
So one is longitudinal strain, and there is longitudinal stress. And what is longitudinal stress again?
The compressive, which includes compressive stress and tensile stress.
And it is a ratio of what and what?
Restoring force by area.
Absolutely. Okay. So we saw what is the longitudinal strain now, right? So moving on to if there is an angular strain, if the deformation is applied parallel to the cross-sectional area, like what we saw here.
Delta theta by L.
The force applied is tangential. So someone wants to attend the call. Sanchita, attend Panecha. So when the force is acting parallel to the cross-sectional area, now this restoring force by area, per unit area, is going to be called shearing stress. What stress?
Shearing stress.
Shearing stress. Now it is acting along the surface or parallel to the surface as a tangent to it. So it's also called tangential stress. In which case, what happened? The body moved like this. Right?
So this is also compressive stress.
Shearing stress. The force is applied. So Depending upon how the force is applied, the name is called as this. So restoring force by area. So here,
Is this also compressive stress, uncle?
is it going to be compressed? There is no compression. Where is the compression? There is an angular displacement in place. Isn't it?
Yeah, this was the same diagram you showed for compressive stress, right, uncle?
I had drawn it, but we are discussing it now. Only we are talking. Okay.
Sir, that diagram was not for
Not for
compressive
compressive
stress,
stress.
right?
Only for the cylinder when it was acting perpendicular only it is compressive stress. Normal.
So that is
Normal.
also called as tensile stress, huh?
Yes. Yes. Tensile
Oh,
and compressive stress.
okay.
There are two
They
things.
they are the same thing.
So there are two things. So, anyways, I'm having this recorded. So if you go over that, you will see that what is the tensile stress, what is compressive stress. Tensile. When do you call this tensile? When it is
Elongated.
absolutely. Compression is when it is compressive stress is when it is compressed. Both acting along the length of affecting the length. So you call it as longitudinal stress or longitudinal strain. So here it is going to be tangential stress or also called as shearing stress. So what will be the strain called? So this is creating a strain, the deformation on the cylinder. So this deformation, the displacement that is taking place. So what is the displacement that is happening here? The displacement is the
Sir, are you writing anything on the screen?
not yet. I'm about to. So this, if you look at the displacement, this region,
Yes,
the
sir.
can has tilted by some, and not only the angle, but it's look at the original shape has now moved by some length, some distance, isn't it?
Yes, sir.
Right. So that delta x, that change delta x to its length. So its length was this L, original length. This ratio delta x by L. So what was the strain in the previous case? Strain. In the previous case, what was the strain? How did we find the strain?
Delta L by L.
Delta L by L. So here, delta x by L is going to be called your shearing strain. This much amount of strain it has undergone, the deformation, right? Which is nothing but tan theta. So if you look at this is delta x, this is your L, this is theta, right? Hypotenuse is this,
Hmm.
adjacent, opposite. Opposite by adjacent is what? Tan theta, isn't it?
Yeah.
Everyone? Hello?
Yes, sir.
Right? Okay.
Yes.
That is your shearing strain now. And theta is nothing but the angular displacement. Okay? So usually theta is small. Okay. Okay. So when you try to compress or when you apply the same kind of a force over a book textbook, like a shearing stress on a textbook, so what happens? Tan theta, the tan theta value is going to be as when theta is very small, tan theta will be approximately equal to 0 only. Sorry, theta itself. Tan zero, what is tan zero? Tan zero is 0, isn't it?
Yes, sir.
Right. So for lesser values of theta, right, the angular displacement will be very minimal. But for a solid sphere, you take a sphere, and that sphere is going to undergo pressure from all the sides. It's, say some solid shape is there. I have some sort of a solid shape which is going to undergo pressure from all the directions. So uniform compression from all the sides. Now the forces are acting inwards. What will happen to this? Its shape will shrink, isn't it? The size is going to
Into a new shape.
uniformly it is applied means it is going to decrease the
Oh,
size of this.
okay.
In which case, if I have a solid sphere place it in a fluid, I have a solid sphere and I'm keeping it in a fluid, and that fluid is under high pressure. Such as this, like the one that we are seeing. We call it as hydraulic compression. So hydraulic compression is just imagine a solid substance placed in fluid under high pressure. Can you arrange the words? Get what I'm saying? A solid
Hydro.
in a fluid under high pressure. The fluid is undergoing high pressure, and in that fluid, you are keeping a solid intact. You have a fluid which is under high pressure. In this, you are keeping a solid substance. Understood?
Yeah.
Yes, sir.
That is referred as what? What kind of compression?
Hydraulic compression.
Hydraulic compression.
Hydraulic compression. So in such a case, what is going to happen? Its volume is going to decrease. In hydraulic compression, we see its volume will be decreased, but without any change in its shape. So if there is a hydraulic compression, it results in decrease in the volume, but no change in shape. You should remember all of these things. Okay?
Okay.
Okay, sir.
So there will be a restoring force in this case also, which we're going to call it as hydraulic stress. So what is this hydraulic stress again? The restoring force per unit area is going to be called hydraulic force. And in hydraulic compression, what is the change we come across?
Volume.
Volume change, yes, absolutely. There's going to be only volume. So therefore, since it is just the volume which is getting affected, we're going to call this strain. In case of hydraulic compression, the strain associated will be called as volume strain, which is the change in the volume with respect to original volume. Okay. So what will be the dimensional formula for this? Advik?
Yes, sir.
Huh? Can you help me with the dimensional formula and the unit for this one, please?
Uh,
Hmm? Sriram? Present?
Dimensionless.
Dimensionless.
yeah, that's what I also thought. It's like VME we cancelled, right?
Dimensionless. And the unit of this will be
Unitless.
unitless. Just a mere number. It's a
Fair enough.
ratio. It's just a ratio. Volume by volume. Okay. So, you done till here? Are we good so far?
Yes,
Yes,
sir.
sir. Good.
Fine. Next is Hooke's law. Whose law?
Hooke's law.
Hooke's law.
What does this say? Okay. For small deformations, wherever the deformation is going to be small, okay, the stress and the strain will be proportional to one another. That's what it says. Okay. This is what the Hooke's law is. Understood? So which means stress is equal to, so if I bring in a proportionality constant, K times strain. Yeah.
Yes.
So this is applicable for most materials. Okay. So most of the materials, since they follow the Hooke's law, this law is also empirical law, also known as empirical law, which is followed by most of the materials. But some materials do not have this. So K times strain is going to be something like what? Y is equal to Kx. What kind of relationship is this? Quadratic, cubic?
Uh,
Advik, Sriram, Prasan, John, Sanjita இருந்தா Sanjita.
it's a linear, right? Relationship.
It is a linear relation. Okay? No quadratic, no cubic. It is linear relation.
Linear.
Okay. But some materials do not exhibit this linear relationship. All right. Next is the stress strain curve. You're going to see stress and strain curve. Let's see what this is. Okay. So the relationship between the stress and the strain on a material for a given tensile stress is what is going to depict the stress. We are going to see that in a stress strain curve. Look at let's take a look at this. So here we can see some deformation, the strain taking place until a linear relationship till some point. So that point can be called as the proportional limit. Until the point, your stress and strain are going to be how? Proportional to one another.
To one another.
Yeah.
Yes.
So this is your strain, and this is our stress. Right. Now, after the point A, what happens after this? If you see from A, after A, there is a deviation from the linearity, and we reach a point which is called this point B. This is point A, this is point B, and the point B is called as the yield point.
What point, sir?
Yield, Y-I-E-L-D, yield point. So here, in this region A to B, we are going to segregate these. Okay, up to A, it is linear. The relationship is linear. A to B, it is not proportional at all. Okay. But still, even though it is not proportional, the body will come back to the original dimension if you remove the force applied on it, or if you remove the load from the body. Okay. At that point, or it is also called as elastic limit. As what? It's called as the elastic limit. Okay. So the stress at this point can be called the yield strength. You can call it as yield strength. All right. Okay. So now, suppose you are going to apply the load more and more. You're going to increase. Excuse me. Now the stress keeps on developing. Okay. The stress keeps you're increasing the thing. The stress builds up and reaches a point C. Okay. At the point C, what happens? C is the point the stress, the yield strength and strain keeps increasing. Okay. So after this point, it's going to keep increasing more and more. Suddenly it keeps increasing more until it reaches a point D. Until I reach point D. Now, after D, it starts to drop down a bit until it reaches the point E, where it cannot tolerate any further, and it breaks. So from B to D, if you see, from the region B to this region, the ability to restore to the original dimension is lost. The body cannot regain its original dimension in this region B to D.
Okay, sir.
Now, the point E, we said, right? The point E. This point is called the fracture point. It's called as the fracture point. Okay. If D and E are close, the points D and E are close to one another. Okay. There is what point the fracture points D as well as E, if they are very close to one another, the material is going to be brittle in nature. What is the brittle material nature? To
Glass,
Nature.
what happens?
they break very easily.
When we give
They
up.
Yeah, but okay, D and E are close. Okay. But if they are far from one another,
then it can be stretched like
ductile. That is where the ductility comes into picture. Okay. If D are far away, then the material is going to be ductile in nature. Do you understand this now?
yes, sir.
Okay. So if you see from the points C and onwards, okay, after B, even if the load is removed at the point C, even if the load is removed here, the material will not have the ability to, it won't have the ability of regaining its shape. Okay. So this is the region where it is to be permanent set. This region is
Person,
called permanent set. It is set. I mean, it is gone. That's it. You can regain its original shape. So such deformation, plastic deformation, the region anywhere between E to E, when the material loses its ability to regain its original dimension, we call it as permanent set. It is also called plastic deformation. We saw a while back, right? Plastic deformation. What happens in that? In plastic deformations, permanent mud. We saw, no?
yes, sir.
If it is able to regain, what do we call it as?
Uh,
Elasticity.
Huh? What was that? Elastic nature.
Elasticity.
Temporary deformation.
Elasticity. We call it as elasticity. Yeah. All right. All right.
okay, sir.
Okay, so we can take a break here. And we
Okay,
can
sir.
continue in our next session. The remaining thing.
Sure, sir.
So this chapter is not going to be difficult. It's a very easy chapter if you follow closely. Just we will have a lot of terms. We will be coming across a lot of ratios, and all are going to be very simple only. Okay.
Okay, sir.
Yeah. So
Sure,
I'll
sir.
see you all tomorrow.
Thank you.
Sure.
Bye,
Bye,
sir.
sir.
Thank you, sir.
Thank you, sir. Take care.
Bye.